Discord has grown into one of the world's largest messaging platform, with millions of users sending billions and now trillions of messages. Finding a message where someone shared a gaming username from 3 years ago? In 2017, Discord needed to build search infrastructure to efficiently index billions of messages while meeting several key requirements. It needed to be cost-effective, to scale, and it needed to be able to select specific messages for indexing. After considering options like managed SaaS solution, which is way out of their budget, they ultimately decided to go with Elasticsearch. Elasticsearch functions as a specialized database optimized for text searches. It's capable of finding not just exact matches but similar words. Discord chose it for its built-in node discovery, automatic chart rebalancing, scaling capabilities, and query DSL for constructing complex queries. To implement their solution effectively, they wanted to avoid the complexity of managing large Elasticsearch clusters. They decided to delegate sharding and routing to their application layer. This would in theory allow them to use multiple smaller clusters instead of a massive one. If let's say one fail, only messages to that specific cluster would be unavailable for surging. With the architecture established, Discord optimized for performance. Since Elasticsearch works best when documents are indexed in bulk, they implemented a queue system. When users send messages in Discord servers, these messages would be sent to a message queue where index workers would collect them in batches and route them to appropriate Elasticsearch clusters based on their server origin. This would create a slight delay before messages become searchable, but a reasonable trade-off since users typically search for historical conversations rather than a recent one, unless you have a goldfish brain like me. Efficiency was further improved by their storage strategy. Discord stored only essential search metadata in Elasticsearch, leveraging an inverted index. The completed message content remains in their Cassandra database with all the details intact. So for example, a message like only the tokenized words like hello and whirl are added to the inverted index, both pointing to the same message ID. This index structure reverses the typical document-to-term relationship, allowing immediate retrieval of all messages containing specific words without scanning the entire documents. To distribute the load effectively across their infrastructure, Discord implemented a load-aware shard allocator using Redis. Each potential Elasticsearch shard receives a score, representing its current load. New Discord servers needing indexing are assigned to a specific shard with the lowest score. As messages are being indexed, the shard score increases proportionally, ensuring that the busy shards with more data are less likely to receive new servers. Finally, to handle massive backlog of historical content without overwhelming their new system, Discord created a two-phase approach. First, messages within the last 7 days were indexed so users can find their message immediately. Then, gradually backfilling older content as a lower priority, like that side project you swore to finish, except Discord actually did it. The system has successfully scaled to handle 26 billion documents across 16K indices, serving millions of Discord servers with stable performance. That's at the end, right? Not quite. As Discord continued its explosive growth, what worked for billions of messages started to show cracks when approaching the trillion mark. The first issue was the cluster architecture itself. More Elasticsearch clusters had to be introduced to handle the load, but this created a domino effect of problems. You see, as more nodes joined the system, the coordination overhead increased dramatically, and the likelihood of at least one node failing at a given time skyrocketed. This node proliferation also exposed critical flaws in their bulk indexing strategy. The real-time index workers would pull batches of say 50 messages from the queue, but these messages were often destined for different nodes across the clusters. If even one operation in the batch failed, the entire operation would fail, forcing all messages to go back into the queue. Some Discord server even grew so large that they hit their license hard limit of approximately 2 billion documents per index. You see, once this happened, all index operations would fail, and Discord only recourse was to work with their safety team to find and delete spam messages. The cascading failures created a vicious cycle. The indexing queue would end up backing up rapidly and would start dropping messages entirely. This meant that some messages never got indexed in the first place and became unsearchable. Definitely not something you want from a search engine. Worst of all, this was inhibiting them from being able to perform basic maintenance. Remember when they said they wanted to keep their Elasticsearch clusters small, hence moving their routing at the application level? Yeah, that didn't quite happen, much like every estimate in the history of software development. Some clusters grew so big that there were over 200 nodes introduced, and that came with all sort of coordination overhead and operational problems. Even patching critical security issues like Log4Shell require taking the entire search system offline. They needed a complete redesign of their search infrastructure that could scale for years to come. The foundation of their solution leveraged Kubernetes, a platform that they were already using successfully for other services. Adopting the Elastic Kubernetes operator to manage their Elasticsearch clusters led to two immediate major benefits. One, cluster configuration could be defined declaratively as code, making deployment consistent and predictable. Two, OS upgrades and software updates can happen automatically with minimal disruption. They also introduced a cell-based architecture. Instead of a few massive 200 plus nodes clusters, they create many smaller clusters organized into logical groups called cells. Each cluster contains 3 specialized node types: the master node for handling cluster coordination, the ingestion nodes pre-process messages before their index, and the data nodes for storing and searching the actual message data. These new configurations allow Discord to match resources need. For example, master nodes can receive more memory to prevent coordination failures, while data nodes can be optimized for storage performance. To solve their queue reliability issues, Discord replaced it with Google PubSub, which provided guaranteed message delivery and could tolerate large backlogs without dropping messages. This meant that even if Elasticsearch fails to index messages, the messages would never be lost. They also fixed their bulk indexing strategy. They implemented batch processing system that would group messages by their destination. For the special case of what they called the big freaking guild, Discord server with billions of messages, they created a dedicated Elasticsearch cell with special configuration. These massive servers receive indices with multiple primary shards, distributing data across multiple nodes in the cluster. This allowed Discord to handle their server beyond the Lucian's 2 billion document limit. They also took this opportunity to implement new functionality. By creating these specialized cells, Discord could now index messages in different dimensions. This enabled a highly requested feature, cross-DM search. By creating a dedicated cell where messages were sharded by user rather than channel, users could finally search across their direct messages at once. Discord's journey from billions to trillions of indexed messages teaches that architecture must evolve with scale. Specialized components create resilience, and embracing managed services simplified operations as you grow. What do you think of their implementation? As always, thank you so much for watching and see you in the next one.